Hello, this is Nikki Jackson from Southwest Tennessee Community College, and I'm covering a few examples from Self-Check 1.2 and Math 1710. For your first example, you have the equation x squared y squared plus 3xy equals 4. What it's trying to determine is whether the graph of the equation is symmetric with respect to the y-axis, the x-axis, or the origin, more of these, or none. So one of the first things that we're going to do is test for the x-symmetry. So my apologies for going back and forth. So here we go with the x-axis. So as far as the x-axis, that's dealing with the x-symmetry, and we're going to determine that by substituting x with negative x. So you may notice right here, everywhere there was an original x, here's the original equation right here. So wherever there was a positive x, we put the negative x. Now pay close attention to how these are. Remember that two negatives give you a positive, so negative x times negative x, still going to get that positive x squared. The exponents still are going to be valid, so that's why it's here. Right here we're using the distribution property, so that 3 times that negative x gives you negative 3x. When you simplify it all together, you have x squared y squared minus 3x equals 4. Where there's no symmetry here because this isn't x squared y squared plus 3x. Again, notice how they're not the same thing. Your next one now, we're going to test for y symmetry. So again, my apologies for moving everything around. So with the y symmetry, we're going to substitute negative y with the positive y, or opposite. Haha. So once again, the exponents are still remain valid. So wherever you see a positive y, you're going to replace it with negative y. So once again, two negatives give you a positive, hence you bring down your exponent. Here we're going to use the distributive property. So positive 3x times negative y gives you negative 3xy, which still equals 4. But once again, it does not equal the exact same original equation. Notice right here you have a minus when you did the substitution, but the original had the positive. Then lastly, we're going to test for the origin. Now when you're doing for symmetry for the origin, you're going to substitute both x and y with negative x and y. So once again, we know two negatives give you a positive. So that brings down back to the original x squared, y squared. Again, using distributive property, we know that two negatives give you a positive. And I left out an x right there, ladies and gentlemen. So, oopsie, here's a mistake. I forgot my x. And let me rewrite over that y, so my apologies. And notice how this is the same as your original equation. Therefore, you have origin symmetry. Now, before we move on to the next one, let me give you a little bit more information about your graphs here. Now, you may notice that that first example that we just concluded with did not have the actual graph there, but it was pertaining to the graph. Now, when you're dealing with the graphs, there's some things that we automatically assume since you're on this level in pre-cal. Some of this was actually taught in Algebra 2, and bits and pieces were taught in TRIG. But since we're all learning differently, some of us may remember it and some of us may not. We're going to assume that you know it, or at least remember. So here's your quick review. When you're doing x squared, that's automatically a parabola. So it looks like a U. Notice how it's meeting right here at the origin. I'm just going to do little arrows right here to indicate that it keeps going and going and going. Now notice how this exponent is an even power. The even powers indicate the number of humps. So the larger the exponent, the more humps you have. Feel free to use your actual calculator to elaborate on this. Now when you're using your calculator, be careful. You may not necessarily see all the humps, but they do actually exist. So once again, when you're using your humps, that's the larger the exponent is going to be. Now we did one of these in 1.1, but when you're dealing with negative x squared, and I got the little equal sign, that graph is going to look like this. The negative indicates that it's going down. That's just like when you do a withdrawal from the bank account. which we definitely do not want to be in the negative in these times. Just a little FYI there. So hopefully you remember some of this. Now while you're quickly writing that down, I'm writing out another example of a graph. Now this graph is pertaining to a fraction. So notice how x is in the denominator. So the more complex the denominator gets, the more curves that you will have. So when we're actually graphing that one's a little bit different than what we normally have, because again, notice how your x is going to be in the denominator, meaning it's on the bottom. That is dealing with a curve. So you have something like this and something like that. So this is just a rough sketch of what I'm doing. I'm not doing it, precise. I'm far from being precise, by the way. And with this particular one, the more complex this bottom part is, the more curves you're going to have. So you might have a curve here, a curve there, and they're all getting closer and closer and closer to the origin. Another graph that is assumed that you already know is dealing with the square root. Now the square root is the same thing as written as x to the 1/2 power, which is another form of the exponent. This one is also dealing with a curve, starting from the origin, but it goes out that way. The shifting comes apart when whatever is either in the radical or outside the radical. Another one that it is assumed that you already know is dealing with the absolute value. So those two bars stand for absolute value, meaning that you're going to have both a negative and a positive version of that. So absolute value is kind of like the parabola, except it's giving you in the form of a V, because it's pertaining to a line. Then we have another example. Notice that your exponent is an odd number. So when you're actually doing these, you still got some more curves, but your curves are more like this. So the more curves you have, the higher the exponent goes. Very similar to your even numbers. Even numbers were parabolas, so you had more humps rather than curves. So that was just a quick side note for you, just so you understand the graphs a little bit better. But back to the examples provided for you. So I'm going to zoom in quickly for our next example. So it's asking you to determine open intervals in which the function is increasing, decreasing, and constant. It is assumed that you've already looked at MyLabs Plus and noticed some of the notes that were provided to you. So you know that what increasing means that it's going up. So notice how it is going up. Remember, we're reading this from left to right. It keeps going up in the direction of infinity. So everybody sees that. Now what we're looking at is the x-axis. Again, look at the x-axis. So for this one, we know that it's increasing in both negative infinity and positive infinity. I'm sorry, negative infinity. I said negative. It's not going down. It's going up. Therefore, it's positive infinity. My apologies. But if we're looking at the x-axis, notice on your y version, you got -4, but your x-coordinate is 0. Therefore, the increasing interval is going to be 0 and positive infinity. For decreasing, notice how when it's going down, because it's almost like it's a roller coaster. You can notice that right there. So right here, negative infinity, negative infinity, negative infinity, negative infinity, negative infinity. Again, look at your x-axis. X-axis where it actually stops. This is also called your minimum, y'all, because that's your bottom part. X-axis at 0, y-axis at -4. So you want negative infinity and 0. And then for your constant part, there is no interval for constants, because let's go back to the graph. Do you see a straight line anywhere? All of these are dealing with some type of curvature. So since there is no straight line, there is no constant. And all of that was just by looking at the graph. Now here we go with something totally different. And I'm just going to take a moment to zoom in for you. So thank you for your patience. So here goes the answer and the actual question, zoomed in on it. So it wants to find the different quotient, finding that f of x plus h minus f of x over h for the following function. That's a whole lot to say. But another way of saying it is just substitute where you're actually using the different quotient. So what we're going to do first is look at all of this. So let me zoom out so you can see it. So our initial function is negative 3x plus 8. That's what we have right here. Using the difference quotient, you're using this formula right here. This right here is a minus sign, by the way. So what we're doing is, wherever we see the parentheses, substitute the actual equation. But right here, not only are we substituting the equation, we're substituting for x. So x right here is going to be x plus h. So wherever we saw an x in the original equation, put x plus h. And then don't forget the 8 because it was part of the original equation. And then we're just using f of x. F of x is the original equation by itself. So you got a lot of substitution going on. So again, this part right here, substitute x as x plus h. So using the distributive property, we're going to have negative 3x minus 3h, bring down your 8. And then for the second part, still use the distributive property as if this was a 1. Two negatives give you a positive, so now we got positive 3x minus 8. Remember, that is a distributive property, so we're distributing everything all over h. Now pay close attention now. Separate things automatically eliminate each other. So you have your negative 3x and your positive 3x. They're gone bye-bye. Then you have your positive 8 and your negative 8. They're gone as well. So cancel each other out. Now we're left with negative 3h over h. You can eliminate or cancel the two h's. FYI, by the way, they really don't necessarily cancel each other out. They just reduce to 1. So now we have negative 3 times 1, or what's just remaining is negative 3. So we just solved that using the quotient rule, or difference quotient. Your other example now has a lot going on in it. So we're going to do a lot of zooming in and out. And some of us might have to use our calculators because we just feel comfortable using them. So here's an example of it right here. And we're only looking at number 4. So let me zoom in again. So you got quite a bit going on right here. You have the function, but this is a conditional function, also known as a piecewise. Now I call it conditional because here are your conditions right here. The function is going to be x plus 5 if x is greater than or equal to negative 5. The function is going to be negative x plus 5 if x is less than negative 5. So I'm saying using the calculator, but we really don't need to use it right now. So let's do it step by step. For part A, you're going to substitute x as 0. Well, let's go back to those conditions. Is 0 greater than or equal to negative 5 or less than negative 5? Well, we're going to use x plus 5 because 0 is greater than or equal to negative 5. So using x plus 5, we're going to let x be 0. So x plus 5 equals 5. Notice how your answer is already given to you. Then your next part. X is going to be negative 7. So go back to your conditions. Is x greater than or equal to negative 5 or x less than 5? Well, let's think about it. Since 7 is less than or equal to negative 5, we're going to use x, negative x plus 5. So wherever we have an x, substitute it in for 7, or negative 7. So negative 7 plus 5 gives you negative 2. Two negatives give you a positive. So your answer here is going to be 2. Then we have the next part. X is positive 2. That's what this indicates right here. So, using your conditions again, we have to compare. Is x greater than or equal to negative 5 or less than negative 5? For since positive 2 is greater than or equal to negative 5, we're going to use x plus 5. Substitute x is 2. 2 plus 5 equals 7. So be very careful with that when you're doing your piecewise. And your last example is pertaining to another graph. So I'm going to zoom in quickly on the graph before I actually show you the problem. Using deductive reasoning, we're going to assume that this is going to be some type of graph with a positive, even exponent. Because notice how everything is going upward. And you have several humps here. In fact, just by looking at the humps, you have 2 minimums. Because that's a downward, that's a downward. And then you got a hump. So you got these valleys and these mountains. And what is actually being asked for is if the numbers, or the numbers if any, which has a relative maximum, and what are they? And if the numbers have a relative minimum, what are these relative minimum? So let's go to part A. So you can see both parts. And again, my apologies for my handwriting. So it's saying find the number of relative maximum. Well, we only see one maximum part. Now notice that these arrows keep going and going and going. Since they're infinitely going, you can't consider those your maximum because they're just going on and on and on. So we're going to look at the one that's actually relative. We actually can see it. So we're looking at what is the x value of the highest point. That's what the little scribble scrabble is. So I'm going to zoom in. So here's your highest point right here. Remember, the arrows don't count. We know the y value is going to be positive 4, but the x value is negative 3. So the number at which f has a relative maximum, that's going to be negative 3. But that second part is asking, find the relative maximum. So this is your x coordinate. This is your y coordinate. So let me write that right there. So that is the y coordinate of the highest point. So pay close attention when you're doing these to your coordinates. Part B, find the number of which any relative minimum. So right here, we see that we have 2 valleys or 2 bottom parts. Both of them are touching the x-axis. So it looks like, no, they don't have a y value then. So it's going to be 0 for their y value. So your first one is going to be at negative 4. Your second one is at negative 2. And since they're not crossing the axis, it's 0. So for part B, the number of which f has a relative minimum is what we just stated. You have your negative 4 and negative 2. But since there is no y value, the relative minimum is going to be 0 and 0. So please make sure you log into MyLabs Plus, which is indicated as stcc.mylabsplus.com. And this is covering your self-check for Math 1710, section L02. This concludes this video, and thank you for watching.